Trying to understand a weak acid titration curve can be very challenging to figure out what chemicals are present at different spots along this curve, and mathematically, how do you deal with this system as you keep adding hydroxide to your weak acid. It's not as simple as strong acids because weak acids make conjugates. So what do we have here? What's actually going on? Well, we've got a lot of different areas, but really we've got three of them that are going to ground us. At the very beginning, we're actually not even on the curve yet because no hydroxide has been added. At the very beginning, point one, we have only a weak acid. So this is just a normal weak acid problem. You have no conjugate yet. Your acid molarity, whatever you're given, it's a weak acid problem. You find the hydrogen, you have the pH. So point one's actually really good. We're not even really here yet. It's just a weak acid. But as soon as you add your first drop of hydroxide, what happens is your hydroxide is going to determine where you go on the rest of this curve. Everything you do from there depends on this neutralization reaction. Because you're adding a base to a weak acid, you have this limiting reactant neutralization problem that always needs to take place. And depending on what is limiting and what's excess and how much and what's left over, you will solve these problems a couple of different ways. So the first thing we come to here is spots 2, 3, and 4. Before we get to the equivalence point at spot 5, so this is where that is. So 5 is going to be our equivalence point. Okay, we'll look at what happens there. We've got a lot of similarities in this region here. Now the equivalence point is when at the end, my acid and my hydroxide are going to be equal. They're both going to be 0, actually, okay? So everything before that, my hydroxide is the limiting reactant, and we have HA and A- in the solution. So anytime from here all the way up to 0.5, we have the hydroxide limiting, we will have a buffer, HA and A-. So these regions are buffer regions. And to calculate the pH, you can use Henderson-Hasselbalch. But then separately, we also want to look at, conceptually, without any math, what species are present. And you get a sense that as the hydroxide goes down, the A- is increasing, and there's a point where they're going to cross. And that makes point 3 the midpoint. And the midpoint is our other grounding point, the midpoint of the titration, because that's the point when your molarity of HA is equal to your molarity of A-. Your hydroxide has neutralized exactly half of this and turned it into conjugate, and that's going to give us our pKa in our Henderson-Hasselbalch equation. So the midpoint tells us exactly at our pKa what the pH is. Then we use before the midpoint or after the midpoint, we're going to be a little lower than the pKa or a little higher than the pKa. So our pH is going to be dependent on that ratio. Below that midpoint, we have the acid molarity is bigger than the conjugate base. And after that, we have the acid molarity is less than the conjugate base. So you can see the acid is going down, the conjugate base is going up. You get at the midpoint, the acid still goes down and the base still goes up. And then you can see what happens at the equivalence point. The acid goes to 0, all the acid is gone, and at the equivalence point, we only have A-. And that is a weak base problem. So the weak base problem, now we need a base equation with A-. And then if we kept adding hydroxide past the equivalence point, we still have A-, but now we have excess hydroxide. And that's a strong base, so that makes the pH pretty easy to calculate because it's just a strong base. You have a strong base and a weak base. Okay, so this really shows us what's going on. I want to go again back to this buffer region though. A little bit below the midpoint, you've got a midpoint and a little bit above it. That gives us a way to conceptually estimate the pH. If we're looking at the midpoint as the pH is equal to the pKa, if I have a little bit more acid, my pH will be a little bit lower than the pKa because it'll be more acidic because I have more acid. And then once I get past that midpoint, my pH will be a little bigger than my pKa because now I have more conjugate base than acid. But in all of this buffer region, the pH is going to be right around, it's circling that pKa because the buffer is protecting that pH wherever the pKa is. So this is how we think about it's a titration curve is really just watching a stoichiometry reaction over time and watching the limiting and excess reactants change. At the beginning, you don't have anything, but once you start adding hydroxide, the hydroxide is the limiting reactant until half of it is neutralized. The hydroxide is still the limiting reactant until all of this is neutralized. And then if you keep adding hydroxide, then you get the excess hydroxide at the top, and that's the easiest point to calculate. So mathematically, you have to kind of navigate your way through this. Conceptually, you need to work your way through this as well. Read carefully, classify everything carefully, and make sure you have your balanced equations set. That is an overview of weak acid titrations. And weak base titrations are also a thing, and they would be all of this flipped upside down.